Yeah, good morning to everybody, and thank you, Joachim, for inviting me to give this presentation and to share some insights with you that we gained during the development of the home storage system MyReserve, which is now being sold by Solarwatt, and which you can see in the background of the title slide. So I was asked to talk about status and perspectives of home storage batteries, and I can talk about status and also on perspectives, because there are some perspectives, at least in Germany, where we had this wonderful government subsidies program in order to ramp up the transition of the electricity system by installing a photovoltaic system both on private homes, also on big areas in the landscape. And this led to roughly 40 gigawatt of photovoltaics being installed during the last 20 years. And this started around 1999. And the subsidies have been granted for 20 years. So all of these subsidies will run out 20 years after installation and commissioning of the PV system. And this opens up a nice market for batteries, because at that time all the investments have been written off and the electricity is available at a cost of €0 per kilowatt hours. So we can see this already. The number of installed home storage system is increasing very nicely during the last years, with expected about 25,000 systems this year. And again, next year we expect about 30,000 to 35,000 systems to be installed, at least in Germany. In Europe, we have about the same amount, so Europe-wide it's about 50,000 systems in 2016. So this is really going to develop as a mass market, and as for all mass markets, the interesting question is what will be the Model T of this mass market. So when the car industry started, this was the first mass product that really was addressing the needs of the customers. In terms of robustness, it was easy to use. There was a really industrial mass production with standardized components, and it was affordable, very important to open up the mass market. And the interesting question is, what will the home storage Model T would look like? There are different answers from different manufacturers, but we can clearly see some trends in this industry. The trends are always set by some market leaders, and this is the share of the systems, at least for 2016, October or so. You see the market leader is still the company Sonnen, with about 27% of the whole market. Then we have the company Senec. Both are on the way since many years, have gained a lot of experience, of course. Then we have E3 DC. I believe some of these products can also be seen here in the exposition. And then some others. And what is the technology behind these? So the cells which are really driving this Model T, they come, as you can see, from volume producers, quality producers. For example, in the case of Sonnen, it's Sony lithium iron phosphate. Senec is still mostly with lead acid, but is now also converting to lithium ion. Then we have E3 DC with Panasonic, and we have cells from LG into these systems. Our company uses cells from SK from Korea. And then again, Sony, LFP, and Samsung 18650 cells. This is an exemption. This is the only company that's Tesla that is using 18650 cells. These are these small cylindrical cells. So you have a wide variety in formats of the cells, in technology of the cells, from lithium iron phosphate systems to over NMC to others. Some are buying modules from their suppliers, others are buying cells and assembling them into modules by themselves. So it's still a broad variety, and the question is what will stay for the next years. Concerning the cell suppliers, there is a strong concentration process ongoing. We had a number of cell suppliers in 2012 and 2014, and they are expected to reduce to 5, 6, maybe 7 in 2018. So it's relatively clear that some companies will survive, like LG, like SK, like Samsung. Lithium Energy Japan is not so clear. Panasonic certainly will survive. And Sony is not listed here because this is a slide made for the car industry, and Sony is not going to supply the car industry, but is delivering cells for home storage systems. So the interesting question is which companies will survive, with which technology, and will they deliver cells or only modules? Some have already made the step over the ocean to Europe. So LG Chem is going to ramp up a manufacturing site in Poland. It's relatively near to the place where Daimler is assembling the car batteries. That's the reason why they have decided for Poland. And Samsung is building a battery plant in Hungary, which is also not far from Western Europe. So these both companies have made their decisions. They want to supply the European market and have placed or are building up production sites in Eastern Europe for cost reasons. And having a look on this, it's somehow strange to hear the rumors from the German politics. This morning I heard that Sigmar Gabriel announced that it should be a nice idea to have lithium-ion cell manufacturing also in Germany. And I think, we can use our energy and our intelligence on other things. This is all over. We should have done this 5 years ago, and Daimler tried to do it with a small company in Kamenz near Dresden, but this is over. The Asians have made the race, and we can only hope that they will supply us with lithium-ion cells in the future. And this is not so clear, since you can observe that some companies tend to integrate upwards on the value chain. So companies like LG, Samsung, Sony, Sanyo, and so on, they all prefer to sell modules instead of cells, because they, of course, want to have the profit for this additional step on the value chain in their own company instead in the company of the home storage manufacturer. So this is not yet clear whether smaller home storage manufacturers will be able to buy cells from this company in the future, or whether they are forced to buy modules. And compared to the car industry, all of the home storage manufacturers are small, and compared to the companies that are going to supply these components, of course. Now for the technology inside, there are many options. We have a large number, a variety of cathode materials for the lithium-ion cells. Not only these three that are mentioned here, there is a number of further materials, and they all differ in specific energy, that is the energy divided by the mass of the system, or in energy density, which is the energy divided by the volume of the system. And they differ also in some electrochemical and thermochemical parameters, like here the onset temperature. This is the temperature at which a thermal runaway of the system starts. That means that it's a chemical reaction, self-propelled, you cannot stop it anymore. And once this cathode material, which stands for nickel, cobalt, aluminium, reaches this temperature, you will observe a thermal runaway in the lithium-ion cell, and there is no way to stop this. And this is the heat of decomposition in Joule program, which will be released then. And there is no way to stop the cell from emitting this heat. And here you can see that the numbers are different for different cell chemistries. And from a safety point of view, one would love to use the system with the lowest heat of dissipation, which is lithium iron phosphate. This is why sometimes home storage manufacturers using this tell their customers this is the safest technology that you can have, which is true if you look only on this number. On the other hand, the onset temperature at which this process starts is still higher in another material, lithium manganese oxide. So from a safety point of view, you could also argue that lithium manganese oxide is the better material because the thermal runaway starts at higher temperature compared to lithium iron phosphate. So looking into the details, it's all not that easy. One can certainly say that nickel cobalt aluminium from a safety point of view is not the best material that you can have. This is the material which is being used in the batteries of the Tesla cars, and which is being used because of its extraordinarily good energy density and specific energy. And there are good reasons to put such batteries in mobile devices, of course. But the point is that failure of a battery starts with evaporation of the electrolyte, not with decomposition of the cathode. The first thing to happen is that the electrolyte is decomposing, and then you have electrolyte vapor pressure building up inside the cell. And the next thing is that the cell opens and that the vapor is coming out of the cell, and then you have a mixture of different electrolyte components, which are some typical components are shown here, and they have flash points which are far below the temperatures at which the cathode starts to ignite, so to say. So the first thing is that the electrolyte ignites, and this electrolyte is more or less the same in all of these battery technologies. So forget about these different temperatures. The interesting thing is the flash point of the electrolyte. And what happens if such a system fails to prevent, for example, the cells from overcharging? You can see here, this is a failure of a home storage system. This was a commercial system with a non-redundant overcharge protection. And you can see here the deflagration of the electrolyte vapor coming out of the cells. They have been overcharged due to a single fault in this home storage systems. And by the way, these are lithium iron phosphate cells, these cells from which still some manufacturers claim they cannot burn, which is stupid, obviously, as you can see here. So this is really a dramatic event, and all of the I would say quality home storage manufacturers take a lot of effort to make sure that this never happens in their systems. Now, why should one have high energy density materials in home storage systems? There are two good reasons. One is that the increasing floor space prices for new buildings, at least in Germany, but I believe more or less this is true for all of Europe, lead to smaller utility rooms. So this is a typical sketch of a new built house, and you have only 4.5 square meters for heating, connection of water, electricity, and so on. And there is not much space left for home storage systems, so you would like to have a high energy density. Another thing is that all these systems will have to be installed by installers, by craftsmen, and they are not allowed to carry more than about 30 kilograms, so you would also love to have a high specific energy in the system. So also for stationary battery systems, energy density and specific energy are important. It's not only for mobile systems, it's also important for stationary systems. This is an example of such a battery module manufactured by my company with an energy of 2.2 kilowatt hours in such a kind of block with 25 kilograms of weight. Since the effect of failure of such a system are really dramatic, it's a good idea to build in any kind of safety measure that you can imagine, and it starts with the cell. Smaller cells, they have an advantage because if a small cell fails, it's only a small amount of energy which is being released. In large cells, the cells should have some internal safety mechanics, like, for example, a ceramic coating of the separator, which is separating the anode and the cathode of the lithium-ion cell. These separators are extremely thin, and it's a good idea to have a really strong barrier there, which is typically made today in the high-quality cells by putting a ceramic coating on the polymer substrate of the separator. And I believe that large cells should have this kind of safety mechanism. And we are going as far as dismantling cells from our supplier and looking into the scanning electron micrograph whether the quality of the ceramic separator is the way that we expect it to be. Another thing is the cycle life of the cells. This is a graph showing the capacity of a cell over the full cycles which the cell made. So full cycle means once fully discharged, once fully charged. And with lithium-ion cells, you observe that the capacity is fading with increasing number of cycles. So the cell is aging, and the cell is losing capacity. And the point where it has lost 20% of its initial capacity compared to the nameplate capacity is typically defined as end of life of the cell. This is the red line shown here. And these are measurements made by the Karlsruhe Institute of Technology from a number of different lithium-ion cells, and all are marked high quality and super long life and so on. It's all lithium-ion batteries, but very different ones. As you can see here, the quality differs extremely in terms of cycle life, from cells which reach 6,000 cycles or even more, and cells which reach end of life after only a few dozens of cycles. Now, how can this be? Well, in this region of low cycle life, you typically find all these 18650 cells. There are no 18650 cells with cycle lives much more than 1,000 cycles. There are additionally cells with low materials purity, coming typically from one big country in Asia. And you have many cells there which include some handmade steps, also accounting for the low quality of these cells. Then you have a number of cells which are in between 1,000 and 2,000 full cycles. In stationary application, that would be sufficient for about 5 to 10 years of operation. And there are some cells made for the car industry in this range. And then we have this, what I would call the green area, which is green, marked green because it's good for the stationary application, which would lead to about 10 to 20 years of operation. And there are still some automotive cells in this range. And the cells we are using is about here, 3,500 cycles. And then there are some cells which are far beyond, and I have no idea for what application they have been developed. I believe they are from the early beginning of the car industry, where all the car manufacturers were very unsure how many cycles they would really need, and pushed the cell manufacturers to increase the cycle life up to limits which they now find out are not needed. So then there are further requirements on the internal resistance of the cells. So these are measurements of the cell's inner resistance. This is the cell that we are using, 50 ampere hours, and you see that after 1C cycle, that means discharging during 1 hour and charging during 1 hour. The cells has a very homogeneous temperature distribution, which is nice, no hot spots on the cell. And the internal resistance is also increasing with increasing number of cycles, which means that the cells is getting warmer and warmer during the aging process over many years of operation. And it's very important that you have to design the thermal management of the whole system according to the internal resistance of the cell at end of life, because still then the system must work. Another requirement is on the recyclability of the systems, which is not so much basic science, but it's a need if the mass market is developing. Increasing numbers of batteries will come back from the market and they have to be treated in an appropriate way. And this means that it should be able to dismantle these batteries in an easy way, which is not easy with many batteries today because the tabs, the leads of the cells are welded. In our case, this is a photo of the inside of our battery module. These are not welded. We have cell connectors that can be disassembled easily, so we can also exchange single cells. And the whole battery module is built in a way that it's completely dismountable. And then you have a large number of norms and regulations that you have to fulfill if you want to sell a home storage system. This is what you have to do. You have to demonstrate conformity to a number of European directives, to German or European norms, and so on and so forth, which is not easy. You have to undergo a large number of tests. This is all very costly at accredited laboratories like TÜV or CTCom or others. And besides this complicated landscape, it's also evolving. So you have also for the norms a roadmap, and this is only a simplified version, so there are many more that are developing, and you have to keep track with your system that you want to sell, that it's fulfilling also the norms of the future. So all these important norms for a home storage system, they are developing further, and you have to make sure that you will still be compliant in the over next year. So this is also a big effort. So to summarize, the home storage batteries, not only for our company, but I guess more or less for all of them, will have to provide the following properties. They have to have a high level of quality and homogeneity according to automotive standards. This is mostly true for the market leaders that we have seen on one slide. They have to have a high level of safety, including some cell internal mechanisms like the ceramic separators. Some additives in the electrolyte can help. There are cells with current interruption device, CID, and so on. More or less, this is fulfilled, but you still see some cells on the market which do not have this. The calendar life should be at least 10 years, better 15 years. So this is the life that the cell is providing without being operated. And the cycle life should be better than 2,000 cycles, preferably better than 3,000 full cycles. This would give the customer about 15 years of lifetime. It should have a small internal resistance, better than 20 micro-ohms per ampere hour. It should be lightweight, so the heaviest component should not be more than 30 kilogram. It should be small volume and footprint, and there is a clear trend towards wall mounting of these systems. It should be low cost, below 500 euro per kilowatt hours, better below 250 euro per kilowatt hours. This is really hard to achieve, and it's questionable whether it could be achieved, but this is a critical point. It should be fully compliant with all relevant norms and regulations, of course, and it should be fully recyclable, which is not given with some of the systems that we see today on the market. So, as you can see, almost all of these requirements are fulfilled, or at least there are some systems that can fulfill them. The big question mark is price. So the main focus of the industry will therefore be on cost reduction. This maybe is bad news for the scientists, because all their nice developments on cathode materials and so on maybe are not appreciated enough, but the big thing to make this really successful is getting the costs down. Yeah, this is what I would like to share with you today, and I'm open for discussion. Thank you very much.